Hello everyone, welcome to module 4, which is on geometrical properties of basically an area. What is a geometrical property? So we know, for example, if you have a geometry, let's say a rectangle with size A and B, then area is one property of this geometry, which is A multiplied by B. But in this module, we're going to talk about two basically property. One is the centroid, which is equivalent of saying a center of an area, and the next topic we're going to talk about is moment of inertia. Let's start with the first one, which is the simpler one. And these two topics, they are essential for the future module which we need to study. We are familiar with a center of mass, basically. We say, let's say if I have a beam, so the concept of center of mass, we say if somebody, let's say, put this beam on a coin, maybe on a sharp point, more like a coin, and let's say we fix this coin to the ground, right? We can say that we can assume that the whole mass is at this tip because everything is balanced, and we can assume that this ruler is basically balanced at this point, and if this is the weight, we can call this point center of mass. That's the idea behind center of mass, right? But when it comes to center of an area, because we don't have any mass or anything, it's not really a physical property to describe it, but we can think of it as something like, let's say this basically rectangular shape that we have. Let's say we have a plate with this thickness T. Let's say this is the plate, and this plate, let's say, have a very small thickness, and let's say, and this time I try to put it on this cone, on this sharp point. So we know intuitively if I draw the two diagonals, and probably if I try to put this cone, let's say if I can draw the 3D for you, something unlike this one, or maybe if I can do a better job of drawing it better. In a moment you will see what I'm trying to achieve. Yeah, if we try to put it, let's say, on a cone, then we can sort of assume that this point is more like the center of mass for this plate, right? This is, imagine this is it's a plate, and this plate, remember, has a thickness, and because it's a physical property, it has a weight, right? But when it comes to an area, we are not really talking about weight. So but using the same concept, we can conclude that in this triangle that we in this rectangle that we had at the beginning, this center is the center of mass, or center of an area, because here we don't have a mass, and we call this point C, or centroid, or center of an area. And our job is to find center of an area, basically. So there are some areas which we know their center. For example, for basically a rectangle, we know the center. For a circle, and also for, let's say, a triangle. Let's say I have a triangle like this one. So for basically a rectangle and for a circle, the center is easy to find out, and we know that from geometry. It's nothing complicated. For a triangle, maybe it's for some of you new. It's new. Let's say if the height of this triangle, let's say to be h, and maybe this side to be, let's say, a. So let's call this one h, and this one let's call it a. The way we find the center of area for this one, we draw this line which is basically the median, and it connect this point at the top to the center of this side. So in other words, this portion is a over 2 and this one is a over 2, and we can prove that the centroid of this area is on this line basically here is h over 3, and we can prove that this is the centroid. So in other words, the centroid is the cross section of the median and a line which is parallel to this side, and if the height of this triangle is h, it's h divided by 3. The proof is in your textbook, but you don't need to basically study it. If you want, the proof of this is in your textbook. So for a special case, let's say a right triangle, let's say if I have a right triangle, in order to find the basically the centroid, this is how we do it. We simply draw one parallel line to one side of this right triangle and one line over here, and keep in mind this is a right triangle, and this side, let's say if the length is a, then this distance is a divided by 3, and the height over here, if it is h, or let's call it for simplicity b, this distance is b divided by 3. So we can prove the centroid for this triangle is this one. So these are basically some simple shape, but when it comes to more let's say complex shape, let's say any complicated shape that has a random basically form. So first of all, we select like an axis. Let's call this one x and y axis, and if this one is x and this one is y, and let's say our job is to find the centroid of this triangle, this complex shape. Let's call it C. So first of all, we show the coordinate of a centroid by x bar and y bar. It's just a convention. Some people use like the term x bar and y bar, and which basically denotes the is x bar, and this distance is called y bar, which is basically the coordinate of this point C, and it's called centroid. So there are general formula which says that this x bar is equal to integral of x dA divided by the integral of dA, and this y bar is integral of y dA divided by integral of dA. And what it suggests basically is that this shape, you can break it down to small tiny elements, which each element has the area of dA, and because it's very small, then you can claim that the center for each point or each element is at the center of this small element. And then they prove that you can use this integral to find the centroid of this complex area. But luckily in this course, we are not going to deal with this complicated shape. Instead, we may deal with shapes that we can break them down to this simpler shape, like small rectangle or triangle or circular shape. And in that sense, then we don't need to use this formula, and instead we use a simple version of this formula, and we say that, well, x bar can be equal to sigma x bar I AI divided by sum of the AI, and y bar is equal to sum of the y bar I AI divided by sum of the AI. So in fact, this is going to be the formula that we will be using in this course, which I will show you in one example. So see, we want to find out the centroid of this area. Already the question gave us the coordinate x and y. We want to find out where is the centroid of this area. Our first task is to break it down to simpler component. So let's say I break it down like that to area 1 and area 2. Let's call this one area 1 and this one area 2. So for each of these area, I know the basically center, right? So for example, for this one, I know that this distance from here to here must be 2, right? Similarly over here, I know that, let's say this distance, the whole thing is 6, so then this distance must be 3, and also I know that this distance must be 0.5. Let's write them down before we forget. So here it must be 2 inches, and over here it must be 3, and also from here this distance must be 0.5 inches. Similarly, I can also say that the distance here must be 0.5. So in other words, I can say that the coordinate of this point is 0.5 and 3, and coordinate of this point is 3 and 0.5. Don't get confused, we have 2 here, right? And then we have 1 inch over there, so the distance, so the coordinate is 3 and 0.5. So basically I can call this one x bar 2 and y bar 2, and I can call this one x bar 1 and y bar 1 basically. So let's go back to the formula that we had. Let's write them down one more time. We have x bar, which is equal to, so let's first write the whole formula. X bar is sum of x bar I AI divided by sum of the AI, and x and y bar is equal to sum of the y bar I AI divided by AI. So that's basically the formula, the general formula that we have. Here we break it down to two areas, so we have A1 and A2. So then it's going to be x bar 1 A1 plus x bar 2 A2, and this formula is A1 plus A2 x bar, so this one we are talking about y, so it's going to be then it's going to be y bar 1 A1 plus y bar 2 A2. So this is y bar 1. All right, so we have all the numbers that we want. We just need to plug and play, right? Let's plug and chuck. So A1 A2, what is A1? A1 is 4 multiplied by 1, or simply let's just write 4 and A2 is 6. Remember A1 here, I'm writing it down here, is 4 multiplied by 1, right? And A2 is 6 multiplied by 1, which is equal to 6. So x bar 1, so we have the value is 3 multiplied by 4 plus x bar 2, which is 0.5 multiplied by A2, which is 6, and it gives me 1.5. It gives me 1.5, and the unit is in inches. And similarly for the second one, 4 plus 6, so I have the y bar 1 is 0.5 multiplied by the area, which is 4, plus y bar 2, which is basically 3 multiplied by area 6. It gives me 2 inches. So we'll see here the coordinate of centroid is at like a point which is like 2 inches, somewhere around here. Sorry, 1.5, which is around maybe here, just approximately, and 2 inches, somewhere around here. So in other words, this is centroid of this area, and as you can see, it is off the area and it is totally okay. Again, remember, the center of an area is a mathematical term, right? When we use the term that to put it on a sharp cone, it was just for you guys to understand the concept, but the center of an area can be off that area, right? Let's move on to the next example. Well, this time here the plate has 2 holes in it. How should we deal with that one? Well, it's very simple, the same concept, except we this time we think that the area has been subtracted. In other words, we say if this one is A1, let's say we can call this one A2, and we can call this one to be A3, all right? And we can say that the total area, which is can be A1 minus A2 minus A3. For each of these area we have the centroid, right? For example, this circle alone, we know the center where it is, we know this circle where the center is, and similarly we know that the this big rectangle, right, the center must be a point somewhere. Sorry, let's move back. The center is somewhere around here, and which we have the basically the coordinate for that point. It must be, so if 6, and over here it must be 10, let's say, yeah, 10, and coordinate of this point also we know it must be, let me write it down here, so it is 3, and what else, 4, and coordinate of this point it is 9 and 16. All right, so here is all the information that we have. We have a1 simply is 12 multiplied by 20. A2 and A3, they are equal. They are pi multiplied by the radius, which is 2 squared. And what about x bar 1, y bar 1? Centroid of the first one, it is 6 and 10. X bar 2, y bar 2. For the second area, it is 3 and 4. And x bar 3, y bar 3. We can see it is 9 and 16. All right, so we have all the information that we need, and now we just plug them in the formula of sum of the x bar I ai divided by sum of the ai. This time we just need to be careful that a2 and a3, they are sort of negative, right? So in other words, when I'm putting them there, here is a1 minus a2 minus a3, and similarly here we just write down x bar 1 a1, x bar 2 a2, and x bar 3 sorry, just here we have to be careful that they are negative, so it is x bar 2 a2 minus x bar 3 a3. We plug this number and we can find x bar, and similarly we can find y bar. Our general formula, y bar I ai sum of the ai, it gives me a1 minus a2 minus a3, y bar 1 a1, y bar 2 a2, and y bar 3 a3, which we have all the information and we can find. As you can see, it's just simply using the formula, but when an area is more like here is a hole, then you need to subtract it. Let's move to example 3. Let's see what it is. We have a beam. This beam is made out of two piece of lumbers, two pieces of wood, and this is basically the cross section that we can see here. So this cross section is we just magnify, basically. This is like a view you can imagine from here. We just magnify this one. All right. So first I need to select a coordinate. So if I want to select a coordinate, and if I'm free to select any coordinate that I want, I'm going to select like a coordinate that its y-axis is on this symmetric line. So basically This is a coordinate that I choose. This is to be x and this is to be y. But why did I pick that one? Because it is intuitive to think that the centroid of this T-shaped area must be somewhere on this line, right? We don't know where it is, but it must be on this line because it's symmetric, right? So if it has to be on this line, then already I know that the x bar must be 0. So I don't need to calculate basically x bar. All I need to do is just calculating the y bar. All right, let's break it down to two areas. So this is area number 1 and this is area number 2. All right, each of these areas we have their area. A1 is 200 multiplied by 25, and similarly A2 it is 100 multiplied by 25, so this one gives me 5,000, and my unit is millimeter squared, and this one gives me 2,500 millimeter square. So what is the centroid of first area? Well, it can be something around here. What about the second area? Well, it's obvious, it's over there. So the coordinate of this guy then is 0 and 100, and coordinate of this guy has to be 0. As you can see, the x for all of them is 0 because it's symmetric, and we put y-axis over there, so it makes our calculation easier. And then this one has to be 212.5. Remember this distance, the whole thing is 25. Let's make sure we didn't make a mistake over here, right? Then this distance definitely has to be half of 25, which gives me 12.5 millimeters, right? So then in that sense I have y bar 1, which is 100, and I have y bar 2, which is 212.5 millimeters. So I need to calculate y bar. It has the formula of y bar ai divided by sum of the ai. Let's put the numbers together. A1 5,000 plus 2,500, A1 multiplied by 100 plus A2 multiplied by 212. And if we do our calculation, and please check my calculation later yourself, it's gonna give you 137.5 millimeters. It means that the centroid for this one is somewhere around here. So that's the centroid of the whole area, a little bit higher than the centroid of the first area, like this distance. It's gonna be basically 137.5 millimeters. All right. So that's all we need to know about this basically centroid of an area. Now let's move to the next topic, which is moment of inertia. But what is moment of inertia? Let's watch a short video from YouTube together.
Let's say we have a plank of wood, which we would like to use to cross a canal. It has a rectangular cross-section, and so we could either use it like we have done here, or we could rotate it onto its side, like this. Intuitively, we can tell that the plank will be stiffer if the load is applied to the shorter side of the cross-section. Some cross-sections are much more efficient at resisting bending than others. The further the material is spread from the bending axis, the stiffer a cross-section tends to be. The cross-section on the right has more material located far from the bending axis, and so is better at resisting bending, even though both cross-sections have the same area. This concept of resistance to bending can be quantified by calculating the area moment of inertia, which is also sometimes called the second moment of area. The area moment of inertia reflects how the area of a cross-section is distributed relative to a particular axis, and so is a measure of how much resistance the cross-section has to bending. The I-beam locates the majority of the material as far as possible from the bending axis, and so is a very efficient cross-section. This is why it is so commonly used in construction.
Yeah, so as you saw in the video, the moment of inertia, or to be exact, we call it area moment of inertia. Area moment of inertia. And the reason is we don't want to confuse this one with the mass moment of inertia. That's a different things. And that topics is when we study dynamics, we deal with mass moment of inertia. That's why in this course, when we say moment of inertia, we are referring to area moment of inertia. It's a physical property which sort of relates to the resistance to bending. So the bigger the moment of inertia for a cross section of a beam, then it means it's stronger in terms of bending, similar like as explained in the video. I'm going to put the links for it's a YouTube video which you can also watch the complete video later. So but mathematically we define a moment of inertia, let's say Ix as integral of y squared dA, and Iy is integral of x squared dA, and Iz is integral of r squared dA. So these are the mathematical terms, but simply if I want to explain them, we break down the whole area here to like a smaller area, which we call them dA. And then you can think of each dA as more like a small weight. And now this small weight, you're calculating its moment about an axis. Remember when we talk about moment, we said always it's about an axis. But this time it is, instead of multiplying it by a distance, we multiply it by the distance squared. Like you see, you have distance squared, right? That's why sometimes people call this one second moment of an area. Second moment of our area. These are just different definition that people use. But here, in fact, remember, we don't have any weight or anything, right? It's just for the explanation. And again, these are not a physical property, they are geometrical property. And these are the mathematical term. And here, remember that is Iz, and sort of this r squared, I can replace it by x squared, y squared, and dA, it gives me Ix plus Iy. And this Iz sometimes is called polar moment of inertia. polar moment of inertia. All right, but we'll talk about the polar moment of inertia later. For now, we just saw from the video that this Ix and Iy, they sort of relate to bending, and we said the bigger these numbers are, the stronger an object to bending, similar to the video that you saw, the piece of lumber that we put over the canal, right? The bigger this Iy was bigger than Ix, and that's why it was stronger in bending. And now the question is how we can basically calculate this Ix and Iy. Do we have to use this integral? No, the answer is no. Simply we for simple geometries, somebody has used this integral and calculate them and tabulated them for us. So we just use the simple formula that we're gonna discuss them in a moment. But before we move further, we should keep in mind that basically the moment of inertia is not a scalar. So it is not a scalar, because remember, for a scalar we just have one number, which is the magnitude, but here also we talk about an axis, right? But also it doesn't have a direction. It doesn't make sense to say a moment of inertia to be positive or negative if you look at this integral, right? So it is not also a vector. It is something between these two, but later I will discuss it more. But for now, just keep in mind it's not a scalar, and also at the same time it's not like a vector, more like a force. It's not like that, right? And its unit is, you can say it's length power 4. So it can be meter power 4, inch power 4, or millimeter power 4, right? It can be its unit. All right. Okay, now let's say how we can calculate it. For simple geometry, so moment of inertia for simple geometry. So for simple geometries, they have been tabulated. In this course, we need basically to know the moment of inertia for a rectangle and a circle. So already we learned that the centroid of a rectangle is here, and a circle same. Let me draw the axis for this one. We call this one x, and we call this one y-axis. Similarly for here, we call this one x, and we call this one y. So x, y, x, and y. So and let's say we know the length here is a and b, and over here let's say the radius of this circle, let's say it is maybe r. Let's call it r. So Ix, moment of inertia about x-axis, this is the formula we're going to use. 1/12 b a to power of 3, and Iy is equal 1/12 a b3. Just keep in mind this power 3 is for the axis that crossing that side, right? So don't confuse with this power of 3. And just to remind ourselves that these axes are passing through the centroid, right? This is centroid, this is centroid. we put this bar over there. All right, and for a circle it has been shown that I bar x, I bar y is equal to pi over 4 r to power of 4. Or in some textbook you may see that it has been shown by diameter. So diameter is like radius half of diameter, power of 4. If you simplify this, 64 d to power of 4. Basically these formula are critical to know. This is for a circle and for a rectangular shape. All right, but two more things we need to know. First one is, what if somebody asks us to find the moment of inertia for an axis which is not this x-axis, it's something like this axis, or maybe it's somewhere around here. Yeah. Luckily there is a formula for that, which we're going to discuss it. Well, let's see what is the parallel axis theorem. Parallel axis, or to be correct, axis theorem. So let's say we have a geometry, any shape can be. Let's say I have a shape, maybe something like that, and let's say that here is its centroid, and we managed to find the moment of inertia about this axis. So let's call this one I. But also I put a bar here to remind ourselves that this moment of inertia is about an axis which passed through the centroid, right? So that's why we call it I bar. Now imagine that we want to calculate moment of inertia about a new axis, like maybe this one. All right, and let's call this one I new. So the theorem, the parallel axis theorem, says that this I new is equal to the I bar plus area, which is area of this geometry, multiplied by L squared. What is L? L is the distance basically between these two parallel axes, and this one is known as parallel axis theorem. All right, so with this theory, when we have the moment of inertia about a centroid, we can sort of transfer that one to a new axis, I new. All right, but how we can use this one? But again, before I use this one, let me also introduce another concept which is known as radius of gyration. Then we solve some example together, so you will realize how you can use this theorem. So what is radius of gyration? Basically, radius of gyration is a simple concept. It says that we define radius of gyration by k, show it by k, and the way we define it, we say k radius of a gyration is equal to moment of inertia divided by an area and a square root of these numbers. Since we have ix and iy, then we also have kx, which is ix divided by a, and ky is iy divided by a. basically is another way to show moment of inertia, which is very common in tables when for different geometry people show the moment of inertia. They prefer to use the radius of gyration, which later in some example you will see how we can use them. But simply if we have kx or ky, we can use this formula to figure out the moment of inertia. All right, now let's solve one example together and see how we can put together all these formula and calculate the moment of inertia for this shape. So this question is asking us to find the moment of inertia about its centroid, around its centroid, and also about its horizontal axis. Okay, that's the plan. So first step, we need to find out where is the centroid. So as I explained earlier in this lecture, to find the centroid we need to decide for a coordinate. So it's up to us, but I prefer to pick a coordinate that its y-axis is passing through this symmetric line, because it makes my calculation sort of easier. So I guess I need to move it a little bit to the left, approximately. Okay, so we can accept that it is a symmetric line, right? So I call this one x and this one I call it y. Now I need to find x bar and y bar. So x bar is 0, but y bar we need to calculate it. All right, so yx bar is 0 because we know this line is symmetric and we know that the centroid must be somewhere on this line. We don't know where it is, but it must be on this line, and if it is on this line it means x is 0. All right, so what's the procedure? As we discussed earlier, we break down this area to basically multiple areas, which sort of we can guess. Already the question did that for us. So we can call this one A1. So let's call this one A1, and let's call this one A2, and let's call this one maybe A3. But since A2 and A3 they are the same, we can also call this one A2. All right, because basically they are at the same level. Now for each of these area we know where is the centroid. For the A1 we know that the centroid is this. What's the coordinate for this system? X is 0 and y is 25. So see, the good things about picking like the y-axis to pass through symmetric is dealing with 0 numbers is easy here, rather than just writing what is the x and so on. All right, what about this A2? And we can sort of guess that, let's say around this line, maybe we put a horizontal line here. This is just for us in order to avoid any mistake. So we know the centroid, basically is approximately here, and this one is over there. And we know the basically the x and y bar for each of them, the coordinate. All right, I pre-calculated all of these distances. Basically, for x bar 2, y bar 2, we can figure out the distance. It's 125 because the whole thing is 150, and we put together all these numbers, we get 75 millimeters. So far all we did is we just find out the centroid for the whole things, which is basically 75. Let's say it's a point around maybe here. All right, I just show it by this big dot here. So that's the centroid for the whole area. Now our job is to find out the basically moment of inertia for this basically shape passing through this line. All right, that's what we want to do next, and that's our main task, because so far we just calculate the centroid. How we can do that one? Well, we know that for each of these area that we have, let's say this one, A1, we know what is the moment of inertia about this axis, right? We have a formula for that, which we just learned. It is a rectangular shape, and the formula is 1/12 and two brackets, one of them power 3. So length of this one is 300, and this one is 50 power of 3. Always for me, in order to avoid mistake, what I do, I write down that two brackets that I have. The one goes to power of 3, which this axis basically crossing it. So let's call it I bar 1, because it is for area 1, and also we put this bar there to remind ourselves that it's passing through the centroid for that area. So the same things I will write down here for I bar 2. It is equal to 1/12, or let me write it down below here. So this one that I'm highlighting, this is I bar 2, and I bar 2 is equal to 1/12, two brackets, power 3. So this one is 50 and this one is 150. Remember, A2 is the one that its width is 50, its height is 150 over here, right? So that gives me I bar 2. All right. Now I need to calculate total I total. So I total is equal to I bar 1. Remember, we are not allowed to add moment of inertia unless they are about one axis. So what we need to do, remember, this is I bar 1, but we are looking after finding moment of inertia about this axis, right? About this I. This is what we are looking after. And we just learned that there is a theorem, it is called parallel axis theorem. So we need to transfer it to that red axis. So it means it's going to give me I bar 1 plus area of 1 multiplied by this distance between these two axes. So what is this distance? Probably we can calculate it. So if from here to here is 25, it gives me 75. You can check my calculation later to make sure that I haven't done any mistake. Power of 2 plus, we don't forget this 2. Remember this A2, there are two of them, so I put 2 here so I don't forget, similar to what we did here at the top here. 2, so I bar 2 plus the same things, same story. I need to transfer this axis I bar 2 to this red axis plus A2 multiplied by the distance, which is basically this distance, and this distance we can figure out is it's 50. Or let me make sure the whole things from the top to here is 125, and if this one is 75, yeah, this distance is 50. So 50 squared. Alright, so we have all the numbers that we need. We have I bar 1 here, we have I bar 2 here, and we have our general basically formula for I total, which we can put together these numbers and find the total moment of inertia for this shape, and the unit is millimeter to power of 4. All right, because all the units was 4. So it looks complicated a little bit, but it's not really. It's just the first step was just finding the centroid, as I did here, and then the next step is for each area like A1, we use the formula that we learned earlier in the lecture to find I bar. We call them I bar because they pass through the centroid, and then we use the parallel axis theorem to transfer it to the one and to the axis that we are interested to know. All right, let's solve another example to make sure that we can find moment of inertia for complex shape like a C shape, T shape, and I shape. All right, so first step, I need to put an axis somewhere, basically to find the centroid. But if we check carefully, we realize that for this area, it's not really that complicated because the shape is symmetric, and most likely we don't need to do probably any calculation, and we can guess that the centroid must be like exactly in the middle here. So that's the centroid, and we are trying to find the moment of inertia about this axis. So again, we didn't need to find the centroid because the centroid was obviously in the middle, and this is our plan. We want to find out moment of inertia about this axis. All right, so we break down this I-shaped beam to 3 area. Let's call this one A1, call this one A2, and this one at the top A3. So basically what I did, I break down this area to 3 area like that. All right, so let me step by step write down A1. So A1 is 150 multiplied by 30. A2 is 20 multiplied by 200, so 200 multiplied by 20. And A3 is 150 multiplied by 30. All right, that's about the area. So for each of them, for each of these area, let's see if we can write down the moment of inertia basically. So for A1, we know the centroid, where it is. Sorry. Okay, we know where the centroid is. So basically that's the centroid. And simply we can write down I bar 1, which is 1/12, 2 brackets, and one of them power 3, the one that the axis is crossing it, 150. So I'll do similar things for the one at the top. So we know that this is the axis that passed through the centroid, like basically the centroid of that, right? Remember, this one is C1, this one is also C2, which happen to be coincide with the total C, like the centroid of area 2 is at the center at this point, and the total centroid of, like the centroid of the total area also at the same point. But this one is C3, right? So moment of inertia about this axis, I will write down here, I bar 3 is gonna be equal to 1 over 12, 2 brackets, power 3, and this 150, and this one is basically 30 to power of 3. All right. So what about the one in the middle? Well, the one in the middle, we know where is its axis, right? A2, I'm talking about A2, which A2 happen to be coincide with A bar, but that's fine. Doesn't create any conflict for us. We call it I bar 2, and I bar 2 is 1 over 12, 2 brackets, same, always I write it down to avoid any mistake. So the one goes to power of 3 is the one that basically this axis is crossing it, which is 200. And the other one is just 20. All right. So we have I bar 1, we have I bar 2, and we have I bar 3. We want the total I. But can we add these three numbers together? No. So in other words, I total, can I write is equal to I bar 1 plus I bar 2 plus I bar 3? No, we are not allowed to do that. Why? Because these things, let me cross it so later you don't make mistake, because they are not about the same axis, and you have to be careful, because they are not about same axis. We are only allowed to add moment of inertia when they are about the same axis. So it means I need to transfer this I bar 1 here, this I bar 3 also here. I don't need to transfer I bar 2 because I bar 2 is already at the centroid there. So let's then transfer I bar 3 and I bar 1 to this axis. How we can do that? Well, we will use the parallel axis theorem. Okay, so I will write it down over here. So I will write down total I, then it's equal to the first bracket I bar 1 plus A1 multiply the distance between these two axes, basically this distance, which we can simply calculate. It's 115. So let me draw it one more time here, like this distance, which is basically 115, right? You can say the whole thing is 200, half of it is gives me 100, and this is 30, half of it is 15, so the distance between these two axes is 115. So 115 power 2. That's I bar 1. What about I bar 2? I bar 2, we don't need to transfer it because I bar 2, see, the distance is 0. It's over there. And what about I bar 3? So this is I bar 3 plus A3, and again the distance between these axes and the one at the center, which probably it's easy to find out that it's exactly equal to the one at the bottom. So in other words, this distance is 115. So 115 square. So we put together all these numbers and we ended up with the total moment of inertia. All right, so let's review it one more time together. First, we break down the whole things to three areas: A1, A2, and A3. We have the area for each. Then for each of these A1, A2, and A3, we know the moment of inertia, the one that passed through the centroid, right? Remember? Only we have the formula for the case when an axis is passing through the centroid. So we have I bar 1, we have I bar 2, and we have I bar 3. But we said we need to be careful. We cannot simply add these three numbers. We need to transfer these 1 and 3 to the center, because remember, we are interested in finding this guy, this total I, right? Let's call it I total, right? We are interested in finding that one, and in order to do so, we need to use the parallel access theorem. All right, so, and here is the last topic. And sometimes when we go to the market to buy an I-beam, and basically these beams they call I-beam because they have, it's obvious, it's shape of an I, and these I-beams usually comes in different forms. Sometimes like the beam is being reinforced like that one, like the middle one is the I-beam, then we put two basically plates at the bottom and top to reinforce it. And we can sort of simplify it as three area, similar to what we had at the top. And we can say, okay, this is A1, like this one is A1, and this is our A2, and this guy is our A3. And then based on the size that we have for this beam, then we start calculating the moment of inertia and so on, similar to what we did in previous example, right? But it's a tedious job, and there are tables that provided us with information which we can use to find the moment of inertia. For example, when we go to the market to buy an I-beam, we realize the I-beams have a code. For example, the market or the online or the seller tells you that do you want, for example, an I-beam of S24 multiplied by 80. So each of these numbers, like they are standard codes, they have a meaning. For example, S may refer to a steel, like the I-beam made out of steel. Then 24 has a meaning, 80 has a meaning. How we can find them out? Here, let's say first we find S24 multiplied by 80. So that's the beam that we are interested. Let's highlight it. So that's the one we want to look at. All right, that's our beam. Let me highlight it. Okay, now we have some information which we can use. First, remember that this part of the I-beam is called web, and this part of the I-beam is called flange. It's just some terminology you should know. Not very critical, but something maybe in future, especially if you are in construction business, can be useful. So then there are other information here which you can find. For example, it says the total area of this I-beam is this number, so you don't need to do any calculation then. The depth, by depth it means like distance from here to here, it's 24 inches. So then you figure out the first number, right? It's called the depth basically. And the width, it's 7 inches. So, and remember this is flange, right? It says it's flange. So the flange, its width is 7 inch. So 7 inches over here. And the thickness is like this number. So you have then the thickness. All right. What else? The thickness of the web also, like here also. You can find out it's 0.5 inches. Anyway, what we were looking was basically this moment of inertia, right? This number about x-axis. So we look at this table and we find out that the moment of inertia is 2100. There are other numbers which later will introduce them to you. But anyway, we are not going to use these tables a lot in this course, or maybe not at all. It is in your textbook, and it is something that you should know. It's available or on internet. For example, if you Google American Standard beams, so you will see these sort of tables, and then for each I-beam or other shapes, the moment of inertia is available. But in this course, mainly we are looking after finding the moment of inertia ourselves. And how we do it, this is a process which you just saw for an I-beam, or the previous example for a C-beam, because it's more like a C or U-beam or whatever you can call it. And for you have the parallel axis theorem here. And for two simple shapes, one is basically a rectangular shape, and also another one is a circular shape. We can find the moment of inertia. All right, that's it for this module. And if you couldn't follow any section, please do not hesitate to contact either me or your TA, Reza.